Chapter 17, we talked about capacitance. We saw already that if we place charges on two conducting plates, equal and opposite charges, like in this drawing here, that there will be a potential difference across the plates, delta V. And the question is, how much charge do we need to put on in order to get 1 volt? This is called the capacitance. Capacitance is how many coulombs per volt. How much charge do we need to put on each plate to get 1 volt of potential difference across the plates? And the answer to that question, it depends on the geometry of the capacitor. So how much charge we get depends on the area. In other words, if we have more area, we can get more charge per volt, or also separation of the plates. Now capacitors can be connected, like resistors can be connected either in parallel, like over here, and capacitors in parallel just add directly. They're in parallel, which is the opposite of resistors. If capacitors are in series, they add inversely. Now once you charge up a capacitor, there's charge on it, and the way to do it is just to connect the capacitor across the battery terminals. There is energy stored in that capacitor. The amount of energy that's stored in the capacitor can be given by one of these 3 equations. It's 1/2 times the charge in each capacitor multiplied by the voltage across the capacitor, or 1/2 times the capacitance multiplied by the voltage across the capacitor squared, or 1/2 the charge in each capacitor squared divided by the capacitance. So when a battery is connected to the circuit, the electrons are transferred from one plate to the other, and the charge and the capacitor plates acquire a net charge. So a typical question you may be asked is, the area of the plates the capacitor is doubled while the distance between them is halved. What happens to the capacitance? Well, again, the capacitance depends on the geometry, right? So if you change A, you get a new capacitance. Let's see, what will it be? If you double the area, it'll become 2A, and you half the distance between the plates. So this new capacitance is going to, 2 divided by 1/2 is 4 epsilon naught A over D. Now it used to be just epsilon naught A over D originally. Now it's equal to 4 times that, so you can see the answer to the question is E, 4 times as much. So in the next chapter, we're talking about current flow, the flow of current. The flow of current is defined as the amount of charge going by in a given amount of time. So if we have a piece of wire and charge is flowing through the wire, the rate of flow of that charge, how many coulombs per second, is what electric current is defined. Now, as the charge flows through a wire, there is a resistance to this flow of charge. In other words, something that slows this down, and that resistance depends on the geometry of the wire. What's it made of? That's rho, the length of the wire, how long it is, and how thick the wire is. Okay, whether the wire is a small area or a large area. The voltage across the plates is given by this equation, Ohm's law, that the voltage is equal to IR, or that the current is proportional to the voltage, directly proportional to the voltage, and inversely proportional to the resistance. and the resistance normally we write this way, and therefore what resistors do is use up energy. Power is defined as how much energy per second. Power is defined the amount of work per second, work per time. So how much work per second is utilized in the resistor is given by one of three equations here. All of these calculate how much work, how many joules per second is burned up in one of these resistors. So let's see if we can do some simple problems. The circuit is connected to a 9-volt battery with net resistance of 40.5 ohms. How much energy is dissipated by the circuit in a time interval of 1 minute? So basically we need to figure out the power, because the power tells me how much energy per second, and therefore in 1 minute the amount of energy is equal to the power times the time, which is 60 seconds, 1 minute. So given voltage and resistance, if you look back at the equations, the equation that we want to use here is that power is equal to V squared divided by R. That's one of the three equations in the previous slide. So V squared is going to be 81, 9 squared. This is V, right? This is V, and this is R. Divided by 40.5. So this gives you power, and therefore the total amount of work, the total amount of energy, W, is going to equal to that number, the power, 80, this is 0.5, divided by 40.5, multiplied by the time, which is 60 seconds. Another problem, let's say we have 16 coulomb. The charge passes through a light bulb in 2 seconds. Find the number of electrons that have passed. So what you need to do is calculate how much charge has passed in the given amount of time. And of course, each charge is contributed to by electrons. So the number of electrons is the charge in one electron is 1.6 times 10 to the minus 19. So delta Q is going to equal to I times T. This tells you the total number of charge that will pass. So we have 16 coulombs So if the question was to find the current, we would find the current using this equation here. The number of coulombs, which would be 16 coulombs in 2 seconds. So that would be 8 coulombs per second, or 8 amps. An amp is a coulomb per second. But this particular problem just asks you to find the number of electrons. So therefore, we already know that 16 coulombs is the number of charge, and 1 electron is 1.6 times 10 to the minus 19 coulombs. So how many electrons do you need to get 16 coulombs? Well, 16 is going to equal to the number of electrons times the charge on each electron, which is 1.6 times 10 to the minus 19. and therefore the number of electrons that you would need would be 16 divided by 1.6, which is 10 multiplied by 10 to the 20th, 10 to the plus 19. And of course that would be 10 to the 20th. Another example of use of the power equation: to burn a light bulb for 24 hours requires how much energy? So power is equal to joules per second, right? That's the wattage of a bulb. And so in this case, 120 watts means 120 joules per second. So how many joules per time, right? Work per time, which is T. So the amount of energy is equal to P times T. How many joules per second? 120 joules per second multiplied by 24 hours, which means it's 24 times 60 minutes per hour times 60 seconds per minute. Okay, and the answer turns out to be 2.8. Well, the answer, converting it to kilowatt hours, it's 2.88 kilowatt hours. You know, you're charged at 12 cents per kilowatt hours. It'll cost you 35 cents or so. Which of the following is equivalent to a unit of resistance? So let's write down V equals IR. So what's a unit of resistance? R is equal to, in ohms, we know it's in ohms, but it's V divided by I. So you can see that this would be the right answer from these choices. In applying Newton's ohm, applying Ohm's law to circuits, we look at how to find the current in various parts of the circuit. So if we start off with something simple, two resistors in series, we know that in series the resistors just add, and the voltage across each resistor also add. So V1 plus V2, those two have to add up to the voltage of the battery. And if the resistors are in parallel, that the resistors add inversely. And what that means is that the more resistors in parallel, the less the total resistance becomes. If we add more resistors, we make the total resistance less. We add another one, we make it even less. And the current, as it goes up, the total current, as it goes up, splits up among the resistors. So right here, part of it goes this way, I1, let's say, and part of it goes that way. Let's say that's I2. So a couple of examples using Ohm's law, particularly in this circuit, very simple circuit. What's the total current flowing? What's the total resistance? What's the total current flowing? So 6 volts is the voltage. The total resistance, they're in series, so total resistance is 4, and therefore the total current is just equal to the voltage divided by the resistance. 6 divided by 4, or 1.5 amps. If these are in parallel, as over here, then the two add inversely. So the total resistance in this particular circuit is equal to 1 over R1 plus 1 over R2, 1 over 3. So that's 3/3, that's 4/3. That's 1 over R total. And therefore the total resistance here was going to equal to 3/4 of an amp. And to find out what the current is, well, the current here, let's call it I1. And the current here, let's call it I2. When the resistors are in parallel, the voltage across each resistor is the same. So the voltage across this one is the same as the voltage across that one, and they're both equal to 6 ohms. So I1 is going to equal to V divided by 1, 6 amps. I2 is going to equal to the same V, but divided by 3, and that'll be 2 amps. So what happens, the total current flowing in here splits up into 2. Part of it goes this way, I1, part of it goes that way. Total current should turn out to be 8 amps. Let's see if it is. The total current should equal to the total voltage divided by the total resistance, which we calculated over here to be 3/4 of an amp. So 6 divided by 3/4 is in fact 8 amps, as it should be. Of course, the more interesting problems are a combination of resistors in parallel and series. So for example, all bulbs are 1 amp. What is the total current in the circuit? Well, there's 1 amp here. I think what they mean here is 1 ohm. Each bulb is 1 ohm of resistance. So if that's true, this is 1 ohm, this is 1 ohm, this is 1 ohm. Let's calculate the total current. The total current is going to equal the total resistance here, the total voltage divided by the total resistance. The total voltage is 10 volts. That's easy. Okay, but what's the total resistance? Well, these two are in series, so they add up to 1 resistor of 2 ohms. This one here is 1 ohm. So these two are in parallel, so 1 over R total is going to equal to 1 over 1 plus 1 over 2, or 3/2. And therefore our total will be the inverse of that, 2/3. So now we can calculate what the total current is by putting in for the total resistance 2/3 ohm. So this is going to equal to 10 times 3/2, or 30 divided by 2, which is 15 amps.